Cool. All right. Yeah, so this is a joint work with Satyen, Kale, Haipeng, Mehryar, and Karthik, and it's about the power of improper learning for logistic regression. So let me go over the setting. So this is an online variant of like binary logistic regression. Everything I'll say also applies to the multiclass case. So for t time steps, we're going to do this process where we receive a feature vector in r to the d. We predict some real valued score that says, say, like how much we like, class 1. We receive the true label, and then our performance is evaluated via the standard logistic loss. Okay. We're going to measure performance with like the usual notion of regret, and the only sort of important detail here is that we're comparing with the benchmarks, which is like the set of all linear functions with norm bounded by b. Okay. What we're interested in is how is optimal regret for this setting determined by the dimension d, the number of time steps t, and in this case, we're most interested in the dependence on the norm bound b. Okay. So let's see, what do the usual algorithms get for this setting? So if we do, online gradient descent, this gets root t regret and scales linearly in the norm bound b. If we do online Newton step, then we get logarithmic regret, but unfortunately we're exponential in this norm bound b. So a natural open question that was posed by like McMahon and Streeter in 2012 is whether you can get logarithmic regret but polynomial dependence on b. And then Hazan, Koren, and Levy showed that no, you can't. If you want logarithmic regret, you need to pay exponential in b. Okay. So is this the end of the story? No. So our sort of first contribution here is to give an efficient algorithm that gets regret that's both logarithmic in b and t. So like, why is this not at odds with this statement right here? The answer is because we do improper learning. So it turns out that like this lower bound only applies to the case where you have to be proper. If you're improper, you don't need to pay exponential. You can just get actually logarithmic. So it's a doubly exponential improvement. And this is tight. So like we have a matching lower bound. You can't improve this any further. Okay. And we have a few applications that I think make like a strong argument that this is like the right way to think about this problem, this like improper perspective. So we resolved like an open problem on the sample complexity of Bandit multiclass classification with logistic loss. And we also resolved an open problem on the sample complexity of online boosting. Okay. And we have a few more extensions, which I think are nice. So we're able to extend this from like the online setting to like the statistical setting, like the IID batch setting, with high probability. So in expectation is easy, with high probability takes like some more work. We also have a sort of bound that extends this type of improvement to like general nonlinear function classes. So like where my benchmark is just some like abstract class of functions. This is based on like chaining. I'm not going to talk about that at all in this talk. You can see the poster or the paper for it. And of course, we also extend this to the multi-class case. So this is important for these applications. So let me like talk about the techniques a little bit. It's like pretty simple. I can basically explain what we do on like one slide. So we're going to approach this through like mixability, which is this concept introduced by Vovk, which sort of characterizes when like a generalization of exponential weights works. So the idea is as follows. So this is like the definition of mixability. So the statement is, for any distribution over the space Z in which I like make decisions, I want there to be some like representative decision I can make, such that regardless of what the outcome is, the loss of my like representative decision is upper bounded by this sort of relaxed loss under the distribution, this like sort of like softmax loss. Okay, and so mixability is important because if you use Vovk's aggregating algorithm, then you get regret that scales with 1 over eta times, say, like log number of experts in the finite expert setting, or more generally, for a setting like ours, say, like log covering number. Okay, and and if you haven't seen this before, you might have seen like X concavity. So this is like a slightly more specialized notion, but X concavity always implies eta mixability, and the X concavity like characterizes, for example, when like online Newton step works. Okay. And so here's like the cute trick, right? Like, so the logistic loss is only e to the minus b x concave, but it's one mixable. And so this is what allows us to go from having like an e to the b in front of our bounds to just, well, 1 in front of the bounds. so like this is like pretty straightforward to see. The point is just you can write the logistic loss as the log loss applied to this sigmoid link function. And this basically tells you that if you do this mapping where you, for a given distribution pi, I'm doing, say, like expectation of sigmoid, but then doing the sigma inverse. Well, the sigma inverse cancels out with the sigma, so you're basically just in the log loss setting. And so you get one mixability. So this is like pretty simple, but it only works in the improper setting. So if I'm in a setting where I have to predict some weight vector and then I see x, this trick does not work. Okay? So like, what is the final algorithm? It's pretty standard. Like, so we're just going to form like the exponential weights distribution over the, like, say, set of b-bounded vectors, and then we're going to compute this prediction using the exponential weights distribution. So to actually implement this efficiently, I need like a log concave sampler. So yeah, efficient, but like it is polynomial time. And if you want to get this to work with high probability for the IID setting, you need to work a little harder. You need to, well, we adapted sort of like a boosting the confidence trick from this paper by Nishant Mehta. So let me spend the rest of the time talking about the applications a little bit. So the first one is Bandit multiclass. So this is this like classic setting where at each time I get some feature vector, I predict one of k classes, and then I'm just told whether I'm right or wrong. So I don't get to see what the correct label was, I just get to see right or wrong. And sort of a standard setup for this problem, if you want like efficient algorithms, is that I'm going to look at linear classifiers as my benchmark, and I'm going to use a surrogate loss, like Hinder logistic. And so this open problem posed by Abernethy and Rakhlin in COLT 2009 is, does there exist an efficient algorithm with root t regret for this setting under the logistic loss? And so our result is like, yes, there is. And the way you do this is in some sense just take the improper logistic regression algorithm I already suggested and just do importance weighting to handle the fact that you have partial information. So it's pretty simple. So the second application is this online boosting setup. This is like introduced by Beygelzimer, Kale, and Luo. So we have like several online classifiers. So we're still in an online multi-class classification setting. We have several online classifiers, and each one is guaranteed to satisfy sort of like a weak learning or an edge over random assumption. So like given any sequence of inputs, they're guaranteed to do, say, like gamma better than random guessing. And what we want to do is like combine these somehow so that we get a proper mistake bound for online classification rather than just like a regret bound. And like an important property that we care about in the setting is adaptivity, meaning that I want my algorithms to not have to know how good the weak learners are. And this is sort of the property that's thought to make like AdaBoost work well in practice, like in the classic like not online setting. And so in this paper that introduced online boosting, they gave an optimal algorithm for the setting, and they also gave an adaptive algorithm, but the adaptive algorithm had suboptimal sample complexity. So basically by sticking this like improper logistic regression algorithm into their framework, we're able to get an algorithm that is both optimal in terms of sample complexity and adaptive. And this also extends to like the multi-class and like ranking versions of the setup. Okay? So just to summarize, the logistic loss, it's one mixable, so that's how you should think about it. And if you do this, then you can get huge improvement in dependence on B by doing improper learning. So like the open problem here that we're most interested in is, can we get like a more efficient and like practical algorithm? Like, can we get the runtime down to something similar to like online Newton step rather than having to do, say like hit and run to implement the algorithm? Yeah. So that's it.
Thank you. Questions? Can you handle other losses?
Yeah, so I think basically anything that has a structure of like log loss applied to like some, like say like Lifshitz link function should be fine.
But it's log or mixability that it's key?
So it's mixability that's key?
Mixability?
Yeah.
Yeah, so it's anything that it's...
Sure. But I mean like, I guess the thing is like the logistic one is just like the most interesting in this case because there's this like big gap in terms of sample complexity. Sure. So I'm just saying like if you do like log loss applied to some other link function, like if you did the what is it called? Not logistic link. The other well-known one, probit. Yeah. Like that, I think would you would see like a similar gap. Yeah.
Okay. Thank you. Thanks again. Thanks again to the speaker and.